in a chemical compound. Okay, so relative number of atoms in a chemical compound. So give me an example of a common chemical compound. Salt, right? And salt's chemical formula or chemical formula is NaCl. Okay, and what this tells us is that we've got one sodium atom and one chlorine atom in this molecule, right? And every single type of salt molecule will have one sodium atom and one chlorine atom. Okay, so we could have 1,000 different salt molecules, but each of those individual molecules will have a sodium atom and one chlorine atom. Okay, and if I look at a compound like water, how many hydrogens do I have? 2. And how many oxygens do I have? 1, right? That tells me the relative number. So for every single water molecule that we look at, there will always be 2 hydrogens and 1 oxygen for every single water molecule. Okay? So that's what we're talking about when we talk about chemical formulae. So when I ask for the chemical formula of something, I'm looking for its symbols that look just like this. H2O, CO2, NaCl. Those are all examples of chemical formulas. Okay? So let's go ahead and take out that periodic table and let's review what a valence electron is. We've talked very briefly about what valence electrons are, but what a valence electron is and how I kind of distinguish an electron is just like that, okay? E with a minus sign because electrons have a negative charge. So when you see this right here, it means I'm talking about electrons, okay? So a valence electrons are electrons in the outermost energy level. Okay, or you can think of it as the outermost shell if you want to. So in an atom, in an element, if we're looking at valence electrons, we're talking about only those in the outermost energy level. Valence electrons are available to bond. Okay, so you can make another little note there if you want to, but these are available to bond. Okay, valence electrons on an element are available to bond. So they want to give them away, they want to take them from others, or they want to share them with another atom to help complete themselves, right? To complete that octet, and we'll talk about here in a second. Okay, so when we talk about valence electrons, that's why we numbered the groups the way that we did. So group 1, which runs right here, group 1 has 1 valence electron, right? Group 2 has how many valence electrons? 2. Group 3 has how many valence electrons?
3.
Yep, and so on down our groups. So as we increase our group number, we increase the number of valence electrons that an element has available to bond. Okay? And what's the ideal number of outer shell electrons that an element wants? 8. Every element wants 8 electrons. So every single thing wants 8 electrons. So you might want to make a note about that. So each atom wants to have 8 electrons. Okay? And this is called the Octet Rule. We're going to talk a lot more about the Octet Rule a little bit later here, but essentially what we're looking for is each element would like to have 8 electrons that is surrounding it. Okay, so that it's complete. So our goal is 8. So that means group 8, since it has 8 valence electrons, does it bond very much with anybody? No, it's already got its complete octet. It doesn't really need to bond. Whereas group 1 only has 1 outer valence electron. So it's going to give away that electron pretty easily so that it has 8 in its next shell underneath. Does that make sense? Okay, so when we talk about valence electrons, if I ask you how many valence electrons does phosphorus have? 5. Phosphorus has 5 valence electrons. It has 5 electrons in its outermost shell that are available to bond. Okay? Yeah, an ion is any atom that has a charge. That means it's given up electrons or it's taken in extra electrons to help itself be available to bond. And so we're going to look at this periodic table of ions, and it tells you every single element's charge, okay, and what its charge is so that it's available to bond based on that charge. Okay? Okay, so we talked about valence electrons. However, valence electrons are different than an element's charge, than an atom's charge. They have different, okay? Just because it has 5 valence electrons doesn't mean that it's got a charge of -5. Okay, that's not how charges work. So I'm going to walk you through where we see a pattern of charges on the periodic table. Okay, if you look at all of group 1, they all have a charge of +1, right? You see that little positive up? Group 1 all has a charge of +1, okay, because it says on your periodic table of ions H+, lithium plus, sodium plus. That little superscript up to the right is giving its charge. So group 1 all has a charge of +1. Group 2 all has a charge of +2. Then we move across to group 3, they have a charge of +3. Okay? And boron is not given a charge on your periodic table of ions because it's a little different. It can have what we call an expanded octet or an unfulfilled octet, so we don't look at boron quite as much, but generally this group has a charge of +3. Okay? Group 4, so group 4 isn't given assigned charges for the most part, but it's either usually +4 or -4. Okay, depending on the situation, and we'll talk about that a little bit later. So it works its way up to 4, and then it starts going in the other direction. Group 5, you see all have charges of what? Or for the most part, have charges of -3. Group 6, most of the time, has charges of -2, -1, and neutral. So this is the pattern of an atom's charge as it goes across. We go 1, 2, 3, +1, +2, +3 most of the time, and we go neutral, -1, -2, -3, and here's where it gets a little bit trickier. Okay? The reason that hydrogen has a +1 charge, the reason all group 1 has a +1 charge is that it has 1 valence electron normally. Okay? But it gives away that electron so easily that it usually hangs out without the electron because it's already given it away. Okay? So it has 1 valence electron, it's given it away. So if it gives away its electron, that means it has a positive charge. So that's essentially where these charges come from, is that we're looking at this state of this element after it gives away electrons or after it takes electrons from other elements. Does that kind of make sense? Yeah. Okay, so that's why hydrogen and them have +1 charges. Same with +2 and +3. They give away their electrons a lot easier than they take them, so they've got a positive charge. Okay. I want you to look at some of the transition elements. What do we notice about the transition elements on your periodic table of ions? They're all positive. Okay, yep, good. What else? Why is the box split in half?
Some elements have like different charges.
Yeah, some elements take on multiple charges. Some elements can behave in a couple different ways. So you look at elements like vanadium, chromium, manganese, iron, cobalt, nickel, copper. Those all have multiple charges. Okay, so you might want to make a note about those in your notes, just talking about elements have the ability to take on multiple charges. Okay, and you might write down some examples of that, like chromium, manganese, iron, things like that. They can take on multiple charges. And we're gonna talk about how we distinguish between each of those types of iron molecules or something like that in the next class, but it has to do with the Roman numeral that's right next to its name. Okay? And we'll get into that next class, but I want you to notice that those types of elements can take on multiple charges. Let's talk about which side of the periodic table are the anions located on. Generally speaking, which side of the periodic table are the anions located? The left or the right? The right side. Okay, from here over are the anions. And what do we know about anions? Are they positively charged or are they negatively charged? Negative. They're negatively charged. So the anions are typically on the right side of the periodic table, and everything else are the cations, right? They're positively charged. They have a positive charge. Okay? So there's a couple different ways that we name these anions or a cation. Okay? So let me clear this out. And we're going to talk about something called a monatomic ion. a monatomic ion? Using what you know about prefixes, what does it mean to be monatomic? It has one atom, right? So a monatomic ion is an ion with only one atom. Okay? And there's ways to name monatomic ions. So to name a cation, they get to just keep their normal name. So cations keep their regular name. Okay, so if I was looking at naming this molecule, I know it's an ion because it's got its charge demonstrated there, and it would still just be called hydrogen. So if I was going to look at another monatomic ion, what would the name of that molecule be? The name of this monatomic ion, what would we call it? Yeah, scandium. So the reason we know it's an ion is because it has its charge here. If it was in its base state, if it was just Sc, we still call it scandium, but in this case it's not an ion because it doesn't give us its charge. Okay, so we know it's an ion because it gives us its charge right here. All right, so cations get to keep their regular name. Anions is where we make a change. Okay, so when we're naming a monatomic ion that's an anion, that's negatively charged, anions, they end in the suffix IDE. Okay, so when we're naming a monatomic anion, it changes the suffix of that word, and it ends in IDE. Okay, so if I was naming this molecule, it's an oxygen molecule with a -2 charge. What would I call it? Oxide. Good. Okay, same if I was looking at Cl-. This is a chlorine molecule with a -1 charge. When we're looking at charges and it's a 1, we don't have to include the -1 or the +1. We just can leave the minus or the plus. Does that make sense? You can drop the 1 only if it's a 1. If it's any other number, you have to include that. Okay, so what would this be called? Cl-. What do we call it? Chloride. Chloride. Okay, so that's if we're naming single ions. The only thing that changes here is that this anions end in IDE. Okay, so if I'm asking you for, to write, what's the symbol for fluoride? What would you tell me? F-1, okay, or just minus. Okay, we can still read this as -1, but we know that we don't have to write the 1 there. Okay? And our charges always go superscript, so they always go to the top and to the right.
How do you know if there's more than a -1 charge?
If it was like this.
I know, but like if you got fluoride and you had to do the abbreviation like that,
Mm-hmm.
and it was like -2
Okay.
charge.
So if I asked you for the symbol for phosphide, what would you tell me? It's P. And what's phosphorus' charge?
-3.
Yep, so we go P -3. Just like that. Okay. You might see some books or some worksheet or whatever write it like this, 3-. It makes no difference, but I always will usually write it -3 so we can see that it's a -3. Okay. All right. Very good. So that's naming monatomic ions. Now what happens when we start to put elements together? Okay, we're going to look at that here in just a second. Of just some common monatomic ions. And all these are listing elements with a positive 1 charge, with a positive 2, positive 3, example, blah, blah, blah. What do we notice about the minus charged elements, the negatively charged elements? What do we notice about their name? They end in IDE. Okay, so that's telling you that it's an ion, that it has a charge. Okay, if you look up in that yellow box on the top right, you'll see the difference between fluorine and fluoride. Okay, so if I would ask you for fluorine, that means I'm just looking for its element at its base state, so just F. If I ask you for fluoride, that includes the charge. Make sense? Okay, so I want you to notice here that the difference between the positives and the negatives is the suffix, IDE. Okay, and then if we look down at these, the second portion of your table here, we see elements that take on multiple charges, and they have a Roman numeral next to them. Okay, that's what we're going to talk about. We're going to get into that a little bit next class, but that's how they indicate an element that has multiple charges. Poly means many, right? So a polyatomic ion is an ion with multiple atoms. And we are going to do some memorization of polyatomic ions. Okay, so that's what you need your flashcards for today, and we'll talk about that at the end. But polyatomic ions are ions with multiple atoms. So an example of a polyatomic ion is something like this. Okay, this is a compound, and overall the compound has a charge. Okay, and we named those a little bit differently. Compounds have polyatomic ions have special naming rules that we're going to go through eventually, but we're going to memorize them first. So this is a molecule that happens to be called phosphate. Okay, but it's a compound with multiple atoms, and it's got an overall charge. Okay, so that's an example of polyatomic ions, and we're going to look at polyatomic ions at the end of class today. A list of some that we need to have memorized. Okay. They always have a charge. Now you've got multiple atoms. Okay, now we're going to start combining elements and what that means and how we name them. So we're going to look at binary compounds. All right, and a binary compound, what do we think the word binary means? 2. Good. So binary compounds are compounds with only 2 elements. Notice that we said only 2 elements, not only 2 atoms, right? We might have multiple hydrogens in a water molecule, but H2O is still considered a binary compound, right? Even though there's 3 atoms total, we've only got 2 different elements represented. That's important. Okay, so binary compounds only have 2 elements, might have multiple atoms. Okay? So, let's look at some binary compounds here. Binary compounds, I want you to make the note that binary compounds must have an overall neutral charge. Must have an overall neutral charge. So when we start combining these elements into a compound, we've got to make sure that overall the compound is neutral. Okay, the charges from one element balance out the charges from another element. Okay, so would we ever probably combine in a binary compound? Will we combine 2 elements with a negative charge? No. A binary compound is composed of a cation and an anion. Okay, so you might want to write that down too. Composed of a cation and an anion. Okay, composed of both a cation and an anion. That means something's coming from the left side of the periodic table and something's coming from the right side of the periodic table. Okay? So we're going to do lots of practice with binary compounds. We're going to start our binary compounds with a compound called magnesium bromide. Magnesium bromide. And we're going to be able to work both forward and backwards. We're going to be able to work from a word version to a chemical formula, and you're going to be able to work from a chemical formula and put it into words. We're going to do both, but I'm just starting out here. Okay, so magnesium bromide. So this would say if I asked you for the chemical formula for magnesium bromide, this is how we go about finding it. Okay, magnesium, chemical formula is Mg. And what's magnesium's charge? +2. So we're going to write them as separate elements first, as separate ions first. Separate ions, separate monatomic ions first. What's bromide? Bromide is Br. What's bromide's charge? -1 or minus, however you want to write that. You can include the 1. That's not a problem if you want to do that. That's completely fine. Okay? But our first step here is to write them as separate ions. Okay? So is everyone on the same page about where those values came from, where the formulas came from? Yeah? Okay. So our next step is going to be to kind of do a cross method. We're going to take the charges and we drop the positives or the negatives and we take the numbers down. So our formula ends up looking like this. Mg1 Br2. Okay, except we don't include this 1 subscript. We leave it out. Okay, so now let's take a look at the overall big picture of what we just did. This formula now, MgBr2, should be neutral overall. Okay, it should be neutral. And what do we know about magnesium's charge? What's magnesium's charge? +2. What do we know about bromide's charge? -1. And we have 2 of them. Right? So if I take a +2 charge plus a -2, that gives me an overall charge of this compound of 0. For magnesium bromide, MgBr2. Okay, we don't leave that 1 in there. We drop the 1 anytime we have a 1 subscript. We drop it so it ends up looking just like this. Okay, does this cross right here make sense to us? Yeah. We don't take the charges with us, the plus or the minus. We only take the number, right? The magnitude of that charge. Okay, let's try another one. Let's try aluminum. Aluminum sulfide. Aluminum sulfide. We're going to write them as separate elements first. And what do we know about aluminum's charge? +3. What do we know about sulfide? So it's S -2. Alright, so we're going to take our 3 and we're going to cross it down here. We're going to take our 2, cross it down here. And we end up with a chemical formula of Al2S3. So then we go back and we double check our charges. Our big picture here is that we're evening out the charges, but this is just a quicker method to do it. Okay, it helps us make a method that's a little quicker to do it. So Al2, what we know about aluminum's charge, it's +3, and there's 2 of them. And we know sulfur's charge is -2, and there's 3 of them. So that gives us a +6 plus a -6, which gives us an overall charge of 0. Okay, that should always happen. We always want these binary compounds to have an overall charge of 0. Okay? Questions here? Okay, let's try one more working from the words and going the other direction. Let's try calcium oxide. So calcium has a charge of +2. Oxygen has a charge of -2. So, if we do our crisscross, leaves us with Ca2O2. What do we know about these subscripts right here? They're even, so we can reduce those. Okay? When they match, we can reduce those subscripts. Okay? Which means we're left with CaO. Do our charges balance out here?
Yes.
Right? We've got a +2 and a -2, which gives us an overall charge of 0. Okay. I want you to notice that for each of our namings, we've started with a cation first, then an anion. So for binary compounds, cations go first, then anions. That's for all compounds. Cation goes first, then anions. Okay, so if you need to put that in your notes for naming, that would be a good idea. Cations always go first, then anions. Cations get to keep their name. Anions end in IDE. Okay, and we always write our chemical formula. Cation first, then anion. So we would never have a formula that looks like this, OCA. That's not how it works. Okay, cation always gets listed first, then our anion. Okay, So if I give you a formula that looks like this, I want you to write the name of this chemical formula. Write the name of this chemical formula. So this is how you'd go about it. We're going to work this through together, and then we will, we'll look at it here. Okay, if I want you to write the name of this formula, what's this molecule called right here? Sodium. And what is sulfide? Okay, that's it. Neither one of these elements takes on multiple charges, do they? No, neither one of them takes on multiple charges. So this is as extensive as we have to get with our name. That's it. We're going to talk about multiple charges next class, but for right now, that's as far as we have to go. If we were trying to look at the charges of these individual atoms, we would do our reverse. Right? We'd take the 1 that we know is here and we'd cross it up. So that would give us Na plus 1 and S minus 2, right? If we were looking for the charges of those individual elements, we would do that process in reverse. Does that make sense? Yeah or no? Maybe?
Yeah.
So write me the name of this molecule, and then underneath that, I want you to write the formula for we've got one of each of these here. Okay, these are separate. So on the top we want the name, and on the bottom we want the chemical formula.
Calcium phosphide.
Calcium phos what?
Phosphide.
Phosphide. Perfect. Do we agree? Yes. Okay, good. Abby, why don't you give me the formula on the second one?
I have SRF2.
SRF2. That's what I have. Do we agree? Right? Because if we take strontium, we know strontium is +2, and we know fluoride is -1. So we're going to take that, cross it down. Very good.